Okay, hi guys. So in this lecture, we'll be seeing second order kinetics. So let's get started. So suppose we have AG plus BG converting into CG. So let's say the initial concentration was A of capital A and again small a for capital B. So concentration at time t would be, let's say we have A minus X and X of C is formed. So rate of reaction can be written as minus dA minus X upon dt divided by stoichiometric coefficient, which is 1, which would be equals to rate of appearance of C, which would be dx by dt divided by stoichiometric coefficient, which is again 1. Or simply we can write that, or we have to also equate this with rate constant times A minus X squared, as it is a second order reaction. So we can simply write that dx by dt is k into 1 minus A minus X square. Okay, next we can integrate by first taking A minus X on LHS and KDT on RHS. So on integration we can write that this will simplify itself to 1 upon, this is A minus X squared. So this can be written into 1 upon A minus X, which would be equals to KT plus C. So let's say when t equals to 0, X was equals to 0, so we can write that C would be equals to, this implies C would be equals to 1 upon A. Just put the values of t equals to 0 and X equals to 0 in this reaction or in this equation. You will get C equals to 1 upon A. So finally we can write the final equation as 1 upon X is equal to KT plus 1 upon C is 1 upon A. So from here we can write that K would be equals to 1 upon A minus X minus 1 upon A divided by T. So this is the K, or the rate constant for a second order reaction. So what would be the half-life of the same? So for calculating the half-life, we know that X would be equals to A by 2. So just put X equals to A by 2 here. So we would be getting K equals to 1 upon T. X would be A by 2, so it would be A minus A by 2 would be A by 2 minus 1 upon A. So this is T half. So T half would be equals to 1 upon K, 2 upon A minus 1 upon A, which would be equals to 1 upon AK. Okay. So this is the T half in this case, when the case was both A and B had the same concentration. Initial concentration was A here. So let's mark it as case 1, where both the initial concentration of both the reactants was A. So in this case, T half was coming out to be 1 upon AK. Now let's say we have another case in which we are again reacting A gaseous plus B gaseous and forming C gaseous, and in this case, let's suppose the initial concentration was different. It was small a in case of AG and small b in case of capital B, and C was initially 0, and let's say concentration at time t was A minus X, B minus X and X. So from here we can write that minus dA minus X upon dt would be equals to, this is the rate of reaction, divided by stoichiometric coefficient is again 1, dB minus x upon dt. Again the stoichiometric coefficient is 1, so just dividing it by 1, it would give us the same term. Then it should be equals to rate constant times a minus x times b minus x. Okay, as this it is a second order reaction and we are considering both the concentration of both the reactants at time t. So from both the equation we can write dx by dt would be equals to k times a minus x b minus x. Again shuffling the equation to accommodate the x terms on the right hand side and dt terms on the left hand, this is on the left hand side, and dt terms on the right hand side. Again integrating it, so we would be getting nothing but after integration. So how do we integrate that? So let's see this. So we can write this as the left hand side as b minus x minus 1 upon a minus x. So what will this give us? This will give us denominator part as the a minus x into b minus x, and in the numerator we will be getting a minus b. So just divided by a minus b. So this is the left hand side. This should be equals to k dt. Okay, so a minus b is just a constant, so this I am taking it out of the integration term, and then we have to calculate or evaluate 1 upon b minus x minus 1 upon a minus x dx should be equals to kt plus c. I am directly writing the output on the right hand side. Then we will be getting 1 upon a minus b, and on this integration we will be getting minus ln b minus x minus of minus ln a minus x, which should be equals to kt plus c. So minus minus gets plused out here, so we would be getting the final equation as 1 upon a minus b ln a minus x minus ln b minus x. This should be equals to kt plus c. So when t equals to 0, x equals to 0, so that we can calculate c here. So it should be ln a by b divided by a minus b. This should be the value of c. Okay, so simply put, we can write that, putting the value of c here, we can write that 1 upon a minus b ln a minus x divided by b minus x would be equals to kt plus c would be ln a by b divided by a minus b. So from here we can write that just taking this part on the left hand side, we would be getting, after simplifying, simple mathematical operation, this would be ln a minus x divided by v minus x multiplied with, so 1 upon b is denominator in both the cases, so I'm directly taking out a minus b and then taking solving the ln part, so this would be b upon a. And if we divide it by t also, so basically this term is kt, and if we divide it by t also, we would be getting rate constant or kr as 1 upon a minus bt ln a minus x b minus x multiplied with b upon a. Okay, so with this we come to the end of this lecture. In the next lecture we'll be continuing more on second order kinetics. So till then, good luck and goodbye.